Hello everybody. Today we are going to talk about how to determine the latent heat of fusion of ice. This experiment is composed of two parts. But before I talk about the procedure and what we are going to do, I want to show you what we have in here. So we have a calorimeter. It's kind of very primitive. Inside of it, as you can see, there is just a can, and the can has this round, this is plastic. It's going to fill in here, and by doing that we are producing a layer of air between the can, which is this, and the outside of it. So that goes in here and just drops in here. And so whatever happens inside the calorimeter is going to be kind of isolated from environment, so hopefully the amount of heat transfer is going to be minimal. Also, we have this agitator because we want to make sure we don't take the lid off as much as we can to help prevent the transfer of heat. And we can agitate, basically mix the mixture inside of it by moving this agitator. Also, we have the thermometer, which we are going to show you the temperature of it later on. But we put that in here and we keep it in there, making sure that it is nice and snug. And but the idea is that you can measure the temperature of the mixture as we continue to do the experiment. All right, so that's the experimental part. We are going to also make some hot water in here on this heater, and we also have ice in here so that we can create cold water as well as the hot water. The balance is in here to measure the mass of the calorimeter when it is empty, and then after we add different temperature waters to it. Okay, so we know that we are going to use this equation. That's the main equation we are going to use. That talks about, that shows the amount of heat required to change the temperature of so much mass of an object with this specific heat by this much increase of temperature. We also know that for melting of ice, the relationship between the latent heat of fusion of ice and the mass of ice and the amount of heat necessary is given by this equation, which is in your lab manual. Now, some of the nomenclature or symbols that we are going to use in our equations are the following. Mass of warm water, M of warm water. Mass of cold water, M of CW, and the temperature of it would be TC. Mass of ice, MI, and the temperature is 0. Okay, we have the ice and the temperature is 0. Then what we'll do, we are going to part 1 of the experiment. We want to find the water equivalent of the calorimeter, M of the calorimeter times the specific heat of the calorimeter. Why we need this combination is because if you look at in here, you will see that the amount of heat that the calorimeter itself absorbs or loses is given by this equation, where M is the mass of the calorimeter and C is the specific heat of the calorimeter. However, as I showed you earlier, this calorimeter is made of so many different parts, and it is almost impossible, if not very, very difficult, to find the specific heat of the thermometer, the agitator, the cork in here, and everything else. So we are not going to be able to just find an M for calorimeter. That's easy, but how about C for calorimeter is not going to be easy. So instead of finding these two terms for calorimeter, we are going to find the combination of these two, because these two always come together. In order to do that, we are going to do the first part of the experiment. So the idea of the first part is just to find M of the calorimeter times the specific heat of the calorimeter as a whole. Okay, so what we do is, this is right in here, all the things that I said earlier. Now, the procedure is going to tell you how we actually do the experiment. And let's go to the procedure first. Okay, so procedure first. We are gonna take first our calorimeter, weight with the balance, so we know what is the mass of the calorimeter, with the thermometer, with the agitator and lid and everything else on it. We record that. Then we are gonna pour warm water. We make water with about 10 degrees above the room temperature, and we pour that into the calorimeter. We try to make it about 1/3 of the volume of the calorimeter filled with warm water. I will tell you later why 10 degrees above. Then, after we did that, we measured the mass of the calorimeter and warm water. And if you subtract this from the mass of the empty calorimeter, you're going to get the mass of the warm water in it. You need that. Wait a few minutes until the equilibrium is achieved, and from the thermometer, which is in the calorimeter, you're going to measure the temperature of at the equilibrium condition. We record that. Then we make about the same amount, about 1/3 of the volume of the calorimeter. We make cold water so that it would be about 10 degrees below the temperature of the room. And we pour that into the calorimeter. We wait until temperature is achieved, or equilibrium is achieved. The temperature at the equilibrium would be T, and we are going to also measure the mass of the total container with cold and warm water so that we can get the mass of the cold water. The reason we do this 10 degrees above and below is because we know that no matter how much we try to minimize the heat transfer to the outside, there will be some that happens. So first we start with warm water above temperature, so we know that some of the heat is going to transfer to outside. We don't want it, but it's a trick that we do in order to reduce the error in our analysis. Then we add cold water with 10 degrees below, such that the heat transfer from outside comes to our calorimeter. And these two, basically, they are going to go in the wash. So that's the reason for that.
All right. Now that you have all the data for the part 1 of the experiment, use the following equation to calculate the combination of the mass of the calorimeter times the specific heat of the calorimeter, which is MCCC. And this equation is the same as the one in your manual under equation 4. In this equation, the right-hand side is mass of the cold water times the specific heat of water times the temperature of the equilibrium of the mix at the end minus temperature of the cold water. And again, minus, the whole thing is minus mass of the warm water times the specific heat of water again, times the temperature of water minus temperature of the mix. Please note that this TW is after the warm water and calorimeter reach the thermal equilibrium. Then the whole thing divided by this same factor in here, temperature of water minus temperature of the mix. Down here it just says the same thing. And so now that you have calculated MC times CC, you're ready to continue with the second part of the experiment, which is finding the latent heat of fusion of ice. So let's continue with that.
In here, so part 2, Okay, oh, by the way, we gotta make sure that m times c that we calculate from the previous stage becomes positive. Because if it's not positive, that means there was too much heat transfer to outside, and we gotta repeat the experiment. Once we did that, now we're gonna go and find LF. In order to do that, first we empty the calorimeter, then we pour water about 15 degrees above the temperature of the room. Again, about 1/3 of the container. We wait until equilibrium is achieved between the container and the warm water, and we get that equilibrium temperature, T1. Then we are gonna add ice, and we keep adding ice, and we monitor the temperature of the thermometer, which is inside the calorimeter, until it becomes about the same as the temperature of the room. That we call it T2. That's the equilibrium temperature. And then we, of course, every time we gotta find the mass of whatever that we add. So we have the mass of all the ingredients. Once we did all of that, then you have all the numbers that we need in order to calculate the latent heat of fusion of ice, which is given by the following equation 3, which is your manual. And this is after you do the energy balance. Latent heat of fusion of ice in here, mass of the warm water, the specific heat of water, temperature before you added ice, and temperature after you added ice, which is almost the same as room temperature, but you gotta record it. Mass of the cold water, mass of the calorimeter times C of the calorimeter, right? Remember, this combination was found earlier. So that is the contribution, basically, of the calorimeter to losing heat. And then this is the amount of heat which was absorbed by the ice. Okay, ice first, mass of the ice times LF, that's first ice melts down, so it absorbs so much heat, and then when it becomes water, this much mass times C of water times basically T2 minus 0, because initially ice was at 0 degree, finally is at T2 temperature of the equilibrium, and so that is this part plus this times that is the amount of heat gained, and this part is the amount of heat that water and calorimeter they lost. Now in the next part, I'm going to show you the input numbers that you need to do your calculation.